Good morning, ladies and gentlemen, if you're joining us from the US. Good afternoon, if you're joining us from Chile or other places in Latin America. And almost good evening, if you're joining us from Europe. We are here today to discuss a very, very important issue, and one that, if you know me at all, you will know that is very close to my heart, which is that of making CSP solar a very competitive alternative, renewable energy alternative with solar thermal storage. This is an incredibly complex and important task that we are all, as a whole industry, carrying out. And I am very happy to have here with me today 4 experts that are working in making CSP extremely competitive. The objective is $50 megawatt hour by 2025. And the people joining here today are Rodrigo Mancilla from CORFO, who's going to be talking about the efforts that Chile is taking. We have Andrew Prescott from the CSP program at the SunShot and the DOE in the US. We have with us also Craig Turchi from the National Renewable Energy Laboratories. And we have also Ángel Fernández from the University of Antofagasta and the Solar Energy Research Center. So we have quite a few people here today. It's very challenging objective today, but one that I am positive we can reach. So before we do anything else, I'd like to ask you, the people listening, what do you think, whether this objective can be hit by 2025? So I'm going to put a poll on your screen, and I'd like you to please vote, just really quickly. Yes, can you please put it up for us, Araceli? Very quickly, just take a quick minute. Please, can you vote in this? Do you think it is possible to achieve the objective CSP at $50 megawatt hour by not 20 to 25, but by 2025? Forget the first part, just by 2025. That was, a mistake that we've made. Just press yes or no. I'd like to hear from as many people as possible that are in the room. As a host and as a panelist, they cannot vote. But Araceli, how are we doing? Do we wait a little bit more, or are we ready to show the results? Ready? Okay, let's show what people are thinking. This is at the beginning of the, and we think that yes, we can hit it. Okay, let's close this for now. For now, it seems like you guys are positive, so I love to hear that. I can still see it, So let's move on then, and let's start hearing. My objective is that by the end of this webinar, you can actually, you've gone back, and hopefully more people will believe this is possible, because we all want you guys to be part of this objective and this challenge. So the first person up is Rodrigo. Rodrigo, please, if you can unmute yourself, share your screen, and tell us how Chile and how your government is going to help the industry get competitive fast.
Hello, everyone. Can you hear me? I'm already online, yes.
Yes, we can hear you, and we can see your screen now.
Okay, great. So you are more optimistic than the people that participated in the last webinar that came mostly from Chile. So that's great news for us. So first of all, I'd like to thank everyone. We have a lot of people already online, and we think that in the coming minutes are going to be even more people participating in the webinar. So this is showing the great interest that many people have in terms of the huge development that we've seen in our power industry in Chile, and also the interest in the opportunities that as a country we have to continue this path. So before starting, I'm going to give a really brief presentation about what we are doing here in Chile. First of all, I'd like to introduce myself. As Belén said, I'm Rodrigo Mancilla. I'm the head of the Chilean Solar Committee. This is a public agency that is in charge of putting in place our solar strategy or solar roadmap, which is focusing mostly in developing a local industry in the country. So for those who don't know well about what is happening in Chile nowadays, let me tell you that we've seen in the last 2 to 3 years a lot of development in solar, mainly in PV. So we have a really small energy matrix that in total has something around 23 gigawatt of installed capacity in total, and of that, close to 1.7 gigawatt is coming from PV. In terms of energy, last month, close to 5% of the total electricity that was generated in the country came from PV. So we are reaching a point in which we are becoming a really solar matrix, and that's good news. However, we perceive that this development is helping us to have more green electrons, but not much more. So we believe that we can do much better than that. So the projects are built using foreign labor, the projects are built using foreign technology that are not really well suited necessarily for our climate conditions. And we think that we can change that, and CSP could be like one of the answers to help our country and to help our companies to be part of this solar revolution in the world. So before going into detail in the presentation, I'd like to ask also the people. So this is not a poll, but it's a question that I hope that you can elaborate and think during this presentation. So in the last 2 years, we've talked with a lot of people in Chile, with the many stakeholders. We've tried to see what is going to be our future in solar, and we decided to be, from my point of view, really conservative in terms of saying that we can be part of this solar revolution and try to do something small here and that. But in the last 6 months, we started to think differently, and we believe that we can become a really leader player in the world, and mostly or mainly in CSP. So the question is, do you think that Chile can become a global leader in solar energy, specifically talking about CSP? Well, we believe that we do have the chance to be a leader, and I'll try to explain what we think about that. So in the last few months, we've seen several publications that have highlighted the amazing natural resources that we have in the north of the country, mostly in the Atacama Desert. So we were in the front page of the Washington Post. There was a journalist that came to Chile to see what is the reality of the solar amazing resources in that place, and he convinced himself that we are also in the best position to lead, at least in CSP. We also appeared in the Financial Times. In the coming weeks, we are going to be appearing in The Economist, and this shows that there is a lot of hype about what Chile can do in this revolution. So we are not talking only about solar, but also about the future green industries of the world, electromobility, energy efficiency, and so on. So this is, we believe, for a really simple reason. So we say that we are somehow in a kind of a perfect storm. We are in the perfect moment to be participating in the revolution of renewables, energy efficiency, and also electromobility. So 2 months ago, we had a chance to participate in the Berlin Energy Transition Dialogue, in which one of the main activities was the launch of a study, a joint study that was performed by the International Energy Agency and also by the International Renewable Energy Agency, which proposed that what should be the role of the renewables in the energy transition. So the study compared the case in which the countries accomplished their Paris commitments which still are going to be insufficient to meet the target of keeping below the 2 degrees Celsius in global warming. So one of the conclusion of that study is the following. So first, the renewable energy share should be duplicated by 2030. So from something close to 18% to 36%. Also, by 2050 should increase at least up to 65%. So the share of renewable energy should increase. At least they say something close between 65% to 70% of the total energy should come from renewables, which in terms of the different technologies, in the case of CSP, this is going to be the installed capacity of CSP should rise up to 720 gigawatts of installed capacity. Nowadays, we have in the world close to 5 gigawatts. So the growth that we are going to be seeing in the coming years of CSP is something that gives us a lot of hope in terms of what can we do in CSP. In the case of photovoltaics, the installed capacity should be by 2050 more than 6,000 gigawatts. Nowadays, we have more than 300 and less than 400 gigawatts. So also in the case of PV, there's a lot of road to be that we need to work in the future. And the last number is in terms of electromobility. So nowadays in the world we have something close to 1 million or 1.5 million of electric vehicles in the roads, and they estimated that should rise up to 850 million electric vehicles. So why the electric mobility, the e-mobility is so important for us? First, we are the main producer of lithium, and the ion lithium battery is the main source of storage for these cars. Second, each electric vehicle uses from 4 to 5 times the copper that is needed nowadays for a conventional car. So there are a lot of interest from the copper mining industry about what is going to be the future of electromobility. And there is one of them that is maybe the most important, BHP Billiton, that last year said that renewables, energy efficiency, and also electromobility will drive the future of the demand for copper. So, and also for lithium. So, our perfect storm, we have a singularity. In the north of the country, in the Atacama Desert, we have, as I told you, the main reserves of lithium, the main reserve of copper, and also the highest solar radiation in the world. So we think that this is our main opportunity, and we are working to try to take advantage of that. So our solar strategy or solar roadmap has something close to 800 initiatives or projects. 50 initiatives with a total budget that is close to $800 million US. And I will show you just 2 of them that are more related with CSP. So the first one is something that we call the Solar Technology District. So it's the idea of developing a really huge power plant. So a power plant that in total is going to have more than 700 megawatt of installed capacity, being CSP the main technology of this power park. That also is going to have in the same place an eco-industrial park. This project is being developed in a public or a state-owned land with the main focus of trying to bring cost down of CSP, so we can supply a really competitive prices with a supply quality close to 24/7. So this could be a really good supply, for example, for mining companies that nowadays are buying electricity from solar, but not so much because they need a really flat supply of electricity. And also it's going to have a technology mix to, as I told you, to bring costs down. So we are focusing nowadays in 4 pillars in this project. We are working with the GIZ and also DLR to mapping the CSP value chain and to see what are the main possibilities for local companies to be part of this industry, supplying in a competitive way the components that this technology needs. We are also working in the site development. So as I told you, we have something close to 26,000 hectares already that are reserved by the National Asset Ministry. We are performing a lot of study, geotechnical, topography, environmental, and solar resource study, and so on. In terms of financing, now we are proposing this project to be financed by the climate change funds. The first one is the Green Climate Fund. So today we have a meeting with our Treasury Ministry to put this project in the first place in the proposal for the GCF. And finally, the energy supply. So this electricity is going to be sold to mining companies in the north of the country, but also to the eco-industrial park that we are planning to build in the same place. So schematically, this is how it should look, this power park. So this is only for purposes of trying to understand what is the concept. But today we are finishing a technology mix study that is showing us that each phases, so we are going to have 3 phases, each of them are going to have 2 CSP towers, a really small share of PV, and at the beginning we tried to see if a best system could be part of the technology mix, but the results are showing that are not competitive. So at least for this project, we are planning to have CSP power plants and also a small share of photovoltaics. So in the corner up, you can see how it should look the industrial park in this project. So we are now ending all the pre-feasibility studies, and we are planning to launch this project in September. So at the end of September, we are having solar phases in the country. So we are planning to launch this project and also showing all the information needed for companies to come to Chile and to bid for each of these lots. So the impacts of this project are estimated to be in terms of total investment, something close to $4 billion in terms of employment, 3,000 in the construction phase, 300 during operation of this power park and power generation park, and also a lot of employment coming from indirect employment. So, and also has a big impact in terms of the reduction of emissions. So we've estimated something close to 800,000 ton CO2 equivalent tons. And the last project is the International Institute for Solar and Mining. So we are nowadays working in 4 main R&D lines. The first one is developing desert PV system for desert, so that these technologies can be well suited for climate conditions in the north of the country. Also, molten salts or energy storage using different minerals that we have also in the salars in the north of the country. Solar metallurgy, so using the sun, trying to not only generate electricity, but also to do some more value-added products coming from copper mainly. And lastly, fuels in the first stage, thinking to produce hydrogen from PV, but also trying to see in the future if we can move forward in terms of producing fuels using reactors and concentrated solar power. So this is really in a brief presentation what we are trying to do. We believe that we can be important part of the solar revolution in the world. We have the money to do at least these two projects, and we are hoping that everyone in the world can help us to also bring CSP costs down and to help the industry worldwide. Thank you, Ellen.
Thank you very much, Rodrigo. Okay, just before I pass on to Craig, just to let you know, we will be distributing the presentations and the recordings of the webinar. By the end of the week, it'll be with you. Any questions and answers that you have, please, if you could put it in the questions and answers box at the bottom. Craig, can you prepare your screen, please? And next, we'll hear from Craig from the NREL, your perspective. And just remember the watch.
Ended up at the end of the presentation.
That's okay.
Okay, thank you. So I'm Craig Tershi. I'm in the Concentrating Solar Power group here at NREL. I'm the Systems Analysis Task Leader, so I get involved in estimating the cost and performance of different CSP technologies. And I'm going to cover 3 topics today. I'll briefly introduce you to NREL Systems Advisor Model, or SAM, and this is the tool that we use for estimating the performance and cost of CSP technologies of various sorts. I'll then provide you where NREL believes the current cost of CSP technology sits based on recent studies that we've done, and then spend much of the time talking about where we see the future of CSP headed in order to hit the aggressive cost targets that we have for the technology as it moves forward. So I'll talk about molten salt primarily as the storage and technology that we're dealing with, although there are some other approaches that I'll also mention. And then I'll introduce the supercritical CO2 power cycle, which is viewed as a power cycle of the future for CSP, and explain why we think that is a good match with CSP technologies. And then lastly, talk about a topic area that is not really technology specific, but deals with how you optimize the value of CSP, which, as probably most of you know, deal with the ability to integrate and dispatch storage. So SAM is a performance and financial model that NREL has developed. It covers the whole suite of different renewable energy technologies that are shown on the left side of this slide. But for our purposes, we use SAM to estimate the performance and the cost associated with CSP technologies. And mainly we're talking about molten salt technologies, be they salt parabolic troughs or salt power towers. So SAM is freely available. You can download it at that website, and there's a number of tools to help you with understanding how SAM operates for training purposes. The last year, we undertook a cost study. So SAM has incorporated in it default cases for each of the technologies. So there's a default molten salt power tower that's included in SAM, and you can open it and run it immediately without knowing anything else about the technology. But we endeavor to keep SAM up to date, not only in terms of performance, but in terms of the cost of the technology in the marketplace. And one of the ways we do that is we survey the stakeholders in the community to get their inputs as to what they feel the current cost of these technologies are. And we did that in 2016. We asked a number of folks, over 100 folks the survey went out to. We got 20 respondents from each of the tower and parabolic trough cases. And as you can see from this table, there was most of the interest actually lied in the power tower technology. Interestingly enough, we didn't get any response when we asked about people's impressions of cost for linear Fresnel systems. So that's, I think, indicative of where the technology space is headed. That is, most of the interest right now is in power towers, and that is because of their potential to be more cost effective than even the trough technology as it exists. So the responses from that survey, I'm only highlighting 2 rows in this table, but this talks about where the respondees felt the current cost of heliostats, this is installed heliostats, and the current cost of the indirect multiplier, or what we refer to as the EPC and owner's cost within SAM. And these were the only categories that really experienced any significant change between the prior study and the study in 2016. And Andrew will go into this in more detail, but the thing I want to point out is that the prior cost for heliostats in SAM was estimated at $170 per square meter. And based on the response from the survey, we lowered that to $145 per square meter, which is continuing a trend that we have seen over the past several years of reduction in the cost of the solar field, which is a major component in the overall cost of the technology. The other slight change we made was increasing this indirect multiplier, and that is indicative of a situation where people are more comfortable right now with the trough technology in terms of the ability to estimate the cost of trough systems. And so they view it a little bit more risky in the building and deploying power tower technologies, which is to be expected for a newer technology. Slide 6 just gives you some sense for the variation in the responses we had to heliostat cost. Most of the respondees that responded said that our cost of $170 a square meter was about right, but you can see that we had people say, no, that's way too high, and we had other people say that that cost was way too low. So there's a great deal of debate right now in the development community about where heliostats are headed. But we do have a number of developers that are confident that they're continuing to bring down the cost of heliostats. So slide 7 is the summary of our update. And what I want to point out here is that SAM has specific configurations within it. And so we've got the trough, parabolic trough case, the molten salt, and the direct steam tower are the ones I'm highlighting here. And when we do the analysis of these three technologies, the one that ends up with the lowest LCOE, or levelized cost of energy, is the molten salt power tower. And that, despite the fact it's got a higher installed cost, it's generating more power. So overall, in the US, our estimate for this technology today is at about $110 per, that should be megawatt hour, I'm sorry, that's a typo there. So $110 per megawatt hour, or 11 cents a kilowatt hour, is our estimate for the current cost. And so you can see the future for CSP is to bring these costs down by about a factor of 2. Within the US, the DOE's SunShot program is pursuing what we're referring to as Generation 3 CSP technologies in 3 different technology columns. And that's shown here as the molten salt, falling particle as the heat transfer and storage media, and the use of gas phase heat transfer fluids. And each of these has their own advantages and challenges associated with them. And then overriding the choice of heat transfer fluid is the requirement for bringing down the cost of the collectors, which is the yellow band across the top, which goes across all technology spaces, as well as the need to deploy more efficient and less expensive power cycles. And I'll talk about the supercritical CO2 Brayton cycle as a opportunity to fulfill that requirement. So I'm going to spend the next couple of slides talking about molten salts and where that technology is headed, and then briefly touch on the particles and the supercritical CO2 Brayton cycle. So one of the aspects of moving the technology into more efficient power cycles is the need to move to higher temperatures in order to realize higher Carnot efficiencies in the power cycles. And if we look at the incumbent solar salt, which is the top row of this table, we note that it's about maxed out in terms of its thermal stability. So its maximum operating temperature is about 600 degrees C. We're not going to be able to move that salt to a higher temperature. Then the remaining rows deal with a number of other salts that are being investigated that do offer the opportunity to go to higher temperatures. The most straightforward and probably the smallest incremental change would be moving from the binary solar salt to a pure potassium nitrate, which is the more stable of the 2 components in solar salt, and gives us the potential to move the temperature up, we think, by perhaps as much as 50 degrees C. And then we get into some more radical changes in terms of salt composition, which are primarily chloride or carbonate based. And those are both capable of moving to much higher temperatures, 800 or 900 degrees C. But as you'll note in the melting point column, usually that comes with a much higher melting point, which offers challenges for operations. And then in the other column, the far right-hand column, is a measure of the relative density and heat capacity. And the relative rho CP, as I'll call it, gives you an indication of how large the tanks have to be, how much salt you need, and how large the tanks have to be in order to have the same amount of energy storage. And the other thing you see here is that these numbers generally are lower than solar salt, which is not what we'd like to see, as we'd like to be able to get the same amount of energy into smaller tanks. So there are challenges here, and one of the things I'll point out is that these salt compositions would in almost every case be better if we could incorporate lithium. You'll see the final salt, the ternary carbonate salt, includes lithium, but lithium carbonate and lithium chloride right now is relatively expensive. And so even though we love its physical properties, the cost of it needs to come down if it's going to be competitive in the marketplace as an option. So the next table just summarizes the benefits and challenges associated with moving to these additional salts. The potassium nitrate, as I said, offers small benefits, but also relatively small challenges. So it's a good, it's a movement in the right direction, but not clear if it's going to get us as far as we need to go in terms of efficiency. The chlorides in general are very stable and low cost, particularly the magnesium chloride blends, but they have a high melting point, require larger tanks, and have the corrosion issues associated with working with a chloride salt that need to be addressed. In contrast, the zinc chloride actually has a low melting point, which is good, but it does not bring the cost benefit with it that the magnesium chloride does. So there's a clear trade-off there. And the zinc chloride also has a measurable vapor pressure, which can add some complexity to dealing with that salt. The carbonates is a very well understood salt because it's been used extensively in molten carbonate fuel cells. Its biggest challenge is the cost of the lithium carbonate in that ingredient. And if prices remain where they are today for lithium carbonate, we don't view this as a viable option because of the cost of that. And then the last bar across the bottom, the thing I want to highlight is that much of the research happening in the US right now and elsewhere has been looking at the chloride salts. And one of the most exciting things that's come out of that is some data showing that if we can maintain the purity of the salt at a very high level within the melt, that the corrosion limits are extremely low compared to what they are in a more industrial grade salt that may have oxygen species in it. So that's an important consideration as we move forward. I want to touch briefly just on the particle power tower design. This is an alternative to molten salts, which brings with it a lot of advantages in terms of not having to deal with corrosive freezing salts. The particles can be very inexpensive. However, you have to deal with now handling a solid media instead of a liquid media for your heat exchangers. The biggest challenge here is designing a new receiver that would use a falling particle design, as well as being able to design efficient heat exchangers to transfer heat from a moving particle into the fluid, in this case the fluid being the supercritical CO2 power cycle. But that's an active area of research. It has a lot of potential, but it also has a lot of challenges that we are just starting to address. And then the CO2 power cycle development, the chart in the upper right really highlights why we're interested in new power cycles. The current power tower design is basically maxed out at about 42% gross efficiency with a reheat steam Rankine cycle. There's opportunity to move to supercritical steam, but that involves a lot of additional challenges based on the size of that technology. It's really designed for hundreds of megawatts in capacity, not a size that is typical for CSP. And so the new CO2 power cycle brings with it the potential of greater efficiency, as you see in the chart here, as well as a more compact power island, which could be a lower capex. And so recognizing that the Department of Energy here in the States has just announced a $100 million cost-shared program to build and demonstrate a 10 megawatt version of the CO2 power cycle. So we're very optimistic about the ability of this power cycle to play with CO2 as a heat source in the future. It also is applicable for nuclear and fossil heat sources as well, which gives us good confidence that it will be successfully invested in and developed. And then lastly, an area that is really not technology so much as in operations and understanding the technology that we're dealing with. We have to make sure that we optimize the design and the dispatch of CSP systems to realize the greatest value within the market where they're being located. And so what's shown here is two power plants of similar design, but designed to dispatch in different fashion. A simple dispatch that just tries to hit as it can price points, and then an optimized dispatch that utilizes forecasting and other algorithms to match up with the highest price points within a given market. And in the blue table, the point I want to highlight is although the optimized design produces less energy and overall in terms of just cost is a slightly higher cost system, the power purchase agreement, which is representative of the value that it is bringing to the market, is lower, meaning that this technology, as it's the optimized technology, is able to return a much higher return on investment for the same type of technology. That is, it can be cost effective even if it realizes a lower power purchase agreement price. So it's essential as we move forward not only to be looking at technology, but also in understanding the markets that the technology is playing in and being able to dispatch to provide the greatest value to those markets. And I'll conclude there and turn it over to Andrew, who will talk a little bit more about collector design.
Correct, Andrew, it's your turn. If you, Craig, can you stop your screen and so that Andrew can share his? Just to let you know, guys, we are running on the low side of time, but the presentations are very interesting. So we will see whether we have any time at the end to take questions, and as much as possible, I'm going to ask speakers when they were done that they answer by text as much as possible, but at least we'll get to hear full presentations from each of the speakers. Andrew, go ahead.
Can you see my screen? Yes? Okay. So I was asked to talk about CSP collectors, just to focus on their costs and what the Solar Energy Technologies Office in Washington, D.C. projects we fund, and spend some time talking about collectors. But first of all, what is Solar Energy Technologies Office, otherwise called SunShot? We actually provide funding over a variety of different programs. Photovoltaics, concentrating solar power, systems integration, soft costs, which are called balance systems, and a tech-to-market group, which is called Innovations in Manufacturing Competitiveness. We work a lot with national labs, industry, and academia, and we provide a lot of funding primarily to drive the cost of solar towards the SunShot targets, which I will discuss soon, which is a 2020 target, not 2025. And to provide a game-changing, cost-lowering R&D to further spur solar development and also to drive the jobs in the solar industry. This is a chart you may have seen before. It's a subset of some of the funding that we provided in the past. If you look carefully in the red, that's the solar field costs that we projected in 2010. The contribution to the overall cost of the LCOE. We are projecting to achieve the SunShot goal, that component has to be reduced from 8 cents to about 1.7 cents, roughly 2 cents, by 2020, not 2025. And as of 2015, that was roughly about 4 cents. And so these are basically a variety of funding opportunities that we have provided over the years. Some of them are very current. This the most recent one, Collect, in 2016, focused on the collective field. I'll talk about maybe 2 of the projects in that funding opportunity, and spend some time talking about some of the specifics about what we are trying to achieve. And so again, the SunShot goal for 2020 is 6 cents, which is about, so it's corresponding to 5 cents LCOE in Chile for 2025. And so, we feel that we are on the path to try to achieve that. There are many challenges remaining, but we will try to discuss some of those in the next few slides. Focusing on the collective field, there are a variety of targets. I wouldn't spend too much time talking about the details of these targets, but feel free to send me questions if you have any questions. Essentially, if you're trying to achieve, and this is assuming the heliostat specific, a cost of $75 per meter squared for the solar field in 2020, in order to achieve the SunShot target of 6 cents per kilowatt hour, or $60 per megawatt hour. But like, as I mentioned before, there are many challenges. U.S. specific, the manufacturing of these solar fields are very labor intensive. Labor costs are fairly high in the U.S. compared to other countries. And so this disclaimer, this doesn't apply to some other countries like South Africa and so on. But there's also concerns about O&M costs, things with handling, material handling, tracking costs, and optical accuracy. And so to try to address these challenges, we have tried to develop a portfolio of projects that specifically try to target to reduce the costs for each of these contributions. For example, manufacturing, we have projects on fundamental physics, looking at trying to understand what drives the behavior of collectors, especially collectors that are not glass-based. We have projects on O&M, super hydrophobic coatings, electrodynamic screens. We have a variety of projects that try to address these challenges. And so here I try to give you a subset of some of the awards that we have funded over the years. Avingo Solar, Bright Source, trying to target manufacturing labor costs. These are advanced manufacturing projects. We have a project that track tracking costs. Penn State is a university in the U.S. that has a waveguide approach to try to collect the sunlight and convert it to heat. We have projects with the National Renewable Energy Lab. I worked a lot with Craig. This project is actually with a PI that is actually looking at the fundamental physics of film-based collectors. JPL, Jet Propulsion Lab. We have projects with universities, for example, University of Arizona, Boston University, Oak Ridge Lab, a national lab, to name a few. So our goal is to actually to help to drive the cost in each of these domains that pose challenges, and to try to help to develop strategic technologies to try to reduce the cost and also to maximize the efficiency at the same time. So now I'm going to talk about maybe some projects in the recent funding opportunity, the COLLECT project. And the goal of the COLLECT project was to basically fund disruptive projects. We define disruptive as projects that are essentially going to drop the cost of the solar field beyond $75 per meter squared in a space where it basically relates to about 33% further drop in the cost. So for example, for a power tower, the heliostat cost for 2020, the projection is $75 per meter squared. We think we can actually fund disruptive projects to get us to try to reach as low as $50 per meter squared if you're assuming heliostat. But again, there's a cost collection efficiency, relationship and a contrast ratio that helps us to basically find projects that not only hit the annualized collection efficiency of the heliostat, but you could have a variety of different types of projects to help us to try to achieve the SunShot goal. Here are two projects. One is the green parabolic trough collector. That's a project that we funded recently, and it's a company called Sun Vapor. And so the goal of that project is essentially to drive down the material and assembly costs of traditional parabolic trough collectors. This is not heliostat. This is actually using a special grade of wood called Douglas fir, and changing the topology of the collector to try to see if we could significantly reduce the cost of the collector itself. This uses a friendly material, as I mentioned before, it's Douglas fir, and it's basically 15% cost of steel. And we believe that it's a very innovative project that takes a different look at how to manufacture parabolic trough collectors. We have another project in the portfolio, and the purpose is the Nucleus heliostat project. It's a linear Fresnel collector project. This is hyperlight energy. So this is a later stage project. Hyperlight uses a lightweight, low-cost material to basically hold the mirror surfaces in position. The primary bearing surface is a waterbed, and it's enclosed on four sides by low-profile walls. and the waterbed is a commodity pond liner. It's a very, very low cost approach, and you know, so we fund projects like this also. So in a nutshell, we are not very we are technology agnostic. We don't say we're going to focus only on heliostats. We focus on heliostats, troughs, linear Fresnel, and any other type of soil type collector that can help to achieve the SunShot target. We are open to funding. In addition to this, we think, and to address the issue of cost, we think, addressing the first question, that 50 cents by 2025 is specific to Chile, especially since Chile is one of the countries that actually, you know, have a large pipeline. You know, so of course, you know, the USA and Spain are basically the market leaders for the CSP. But of course, Chile and China are catching up, right? And so, you know, Solar Reserve, as you know, has a variety of projects that they believe that can help to achieve the SunShot goal, and also target maybe the Chilean goal. You know, Solar Reserve has the project in Copiapo. It's a 240 megawatt project. They believe, you know, that they could achieve close to $63 per megawatt hour. You know, so that's getting towards the SunShot goal, and also that could possibly get close to the Chilean goal. You know, they also believe that they have a project in Nevada in the U.S. that actually they claim that it will also have a lower cost than natural gas power plants. So to answer the question, you know, SunShot is very optimistic that with aggressive funding, we could achieve the cost that you guys are talking about today. And so by doing the projects that I mentioned in the portfolio earlier, we believe adjacent technologies, for example, glass point solar, you know, those type of applications will further increase the deployment. We believe by continuing to use advanced manufacturing, especially for labor intensive and high cost labor markets like the US, we think that could also address the reduction in cost of the solar field. That's all I have today.
Wow, excellent. That was really good timing. The last speaker for today is Angel Fernandez, and once that we've heard from Angel, then if you can just take off your screen, please, Andrew, and we can allow Angel to share his. After that, we'll see whether we have any time for questions and answers. We are doing as best as we can, trying to answer them from the question and answer box by text. Angel, you ready? Here we go.
Yes, here we go. Hi, in my presentation, I would like to talk that what we are doing in Chile in order to obtain this objective of $50 per megawatt hour and the challenges for thermal energy storage. I would like, I would like to start with this slide. We are comparing this objective with the SunShot goal, fixed in 6 cents per kilowatt hour, and what we need to do if Chile wants to obtain this 5 cents per kilowatt hour objective. And I think that we need to obtain more or less this price, and in my case that we are working on thermal energy storage, we are trying to obtain a final cost about 0.8 cents per kilowatt hour. The main advantage in Chile are the raw materials present in the Atacama Desert and the higher radiation that we have in the north. Okay. In this slide, you can see all the raw materials that are present in the Atacama Desert. We are trying to develop new molten salt and trying to obtain new formulation for thermal energy storage. As you can see, we have a lot of sulfates, carbonate, of course, nitrate. And from Antofagasta University, we are trying to develop new molten salt for thermal energy storage. Right now, our bet is the proposal of lithium nitrate as thermal energy storage material. The main property that we are obtaining with this additive, we have a low melting point, The thermal stability of the molten salt is also increased, and the key point is the heat capacity of this salt. And we think that we can store more energy in a lower volume, and the corrosion potential is also an advantage because the corrosion that we are obtaining with this ternary molten salt containing lithium nitrate is lower compared with the binary solar salt. The main handicaps that we have are viscosity and the cost of this salt. The viscosity is we are testing this salt, and viscosity is more or less similar to binary solar salt currently used in this technology. And the main problem, I think, is the cost. Of course, we know that the CSP technology is going to higher storage temperatures. So in the Atacama Desert, we have also different carbonates and chlorides that could be used for this new generation of CSP plants. In this slide, you can see the results that we are obtaining in this ternary and quaternary molten salt containing lithium nitrate and calcium nitrate. And at this time, we are focused on the last mixtures containing 30% of lithium nitrate. And the world temperature range that we are obtaining is about 120 to 696 degrees. Viscosity, as I mentioned before, is more or less the same compared with the solar salt. Corrosion is a great property in this ternary salt, so corrosion is lower. So we could think in use an expensive material for the containers. And the key point is the energy density that we are obtaining with this formulation. So we could store more energy in a lower volume and use low quantities of salt in the tanks. In Antofagasta University, we have a molten salt loop in order to test this formulation in a large volume. This is the final configuration. It's a 1 ton of capacity tank, and the idea is flow the salt through the pipes and check what is the minimum temperature that this new molten salt is flowing, what is the minimum temperature flowing correctly without decomposition, and what is the maximum temperature without decomposition, okay? In the upper part, we have a dynamic corrosion setup in order to study the corrosion in a more realistic test and check what is this corrosion with the salt flowing through the pipes, okay? This time we melt 800 kilograms of salt, and as you can see at 160 degrees more or less, the salt is liquid. So I think that this is a good result for us. And the main handicaps are the higher cost, and there are not industrial companies able to produce lithium nitrate in a large amount. That's the reason why we are working with Albemarle Corporation. It's an important company present in the Salar de Atacama that is producing different lithium compounds, and our objective is produce this lithium nitrate in a first stage from the brines in the Atacama Desert, and avoid all the lithium batteries market, and trying to propose a lithium nitrate with a low cost. Okay. We have performed different economical studies, taking into account the higher radiation that we have in the north of Chile and the thermal properties of this ternary molten salt containing lithium nitrate. And as you can see, we compare three locations, three places. The Atacama Solar Platform is a research place close to Antofagasta, the south of Spain and California in US. And well, the results for the LCOE are more or less in the range that we are trying to obtain, about 8 cents per kilowatt hour. So the LCOE for the CSP plant on the Atacama Desert would be 30% lower. Finally, the conclusions, we think that these substitutes could be obtained using these lithium-based salts. We are increasing the world temperature range, and we are confirming these properties in a large scale in this pilot plant. But lithium nitrate is necessary, and also, of course, we need to perform more accurate studies, conversion of electricity generation cost and performance. And that's all.
You actually were the fastest of all then. We still have a few minutes, I guess. That's, I'm very happy right now. Well done. I just wanted to see whether there was any questions there pending that maybe we can answer live now. There's one question for Craig here. Thanks for the interesting presentation. It says, what about the liquid metal alternative as a heat transfer fluid, sodium, for example? Thanks in advance, it says. Craig, do you want to answer that slide?
Yes. Sodium has been considered as a heat transfer fluid, and there's active work in Australia that's pursuing that. Sodium, as the person who asked the question probably knows, is an excellent heat transfer material, much better than any of the salts that we've been looking at. But it comes with it some safety constraints. And the U.S. program has decided not to pursue sodium, although there are others in the world that are doing that, and I think it is an appropriate heat transfer fluid option.
Well, we have had a lot of questions, but you guys have been doing such a great job, because actually we had an hour max and we're literally 3 minutes away from it. So I don't know if any of you wants to give any, I know, Rodrigo, you've had a million questions and I can see your hands up. So do you want to give us a little bit of maybe tie up of what people have been asking and the answers?
Yeah, I've seen a couple of questions that are related to the Cerro Minador or Abengoa project that is being built in the north of the country. So I just want to tell you that that project restarted construction like 3 or 4 months ago. So nowadays we have a new company that is called Cerro Minador, and it's a joint venture between EIG, that is an investment fund, an American investment fund, and also Abengoa is participating, but as a EPC contractor. So this project should be, at least the photovoltaic part of the project should be connected to the grid in the next month, and we are hoping that the CSP tower should be online by 2019. So the project already restarted construction. We are really happy that we're going to have the first CSP tower working, operating in the next 2 years. And we are hoping also that the rest of the projects, the ones from Solar Reserve and also from Sener, could be developed and built in the next 2 to 3 years.
Okay. We have, sorry about that, an extra question here, which I guess Angel, Andrew, what happens if and when the salt freezes? What keeps the pipes and pumps from bursting? Suppose this is something quite generic that a lot of people can answer, but can we give a quick answer here, because we really need to go in a couple of minutes?
Okay. Well, there are heat resistant in the plant in order to avoid the freezing of the salt, but we are working with ternary salt with low melting points. So, for example, for binary solar salt, if the melting point is about 223, the operation in the plant never go low at a low temperature about 220. So with this lithium salt, if we have a melting point about 130, we think that we could maintain the temperature, the minimum temperature, about 170 degrees. So it's important to avoid the freezing, but with a low melting formulation, I think that will be easy.
Excellent. Okay, Andrew, since you are the only one that hasn't answered the question now, do you want to kind of like give us some last thoughts before we close off? So you're the last one to speak, so make sure it's wise.
I had to unmute myself. Yeah, sure. I saw a question about, first of all, the how to decide between using parabolic trough and I guess that means the power tower plant. I mean, that's a specific question for a company that is familiar with the power tower, which is much higher temperature, much higher efficiency. And I think, that's something that I can't answer. It depends on the developer who's doing it. Some developers take less risk with the parabolic troughs. Those are much more developed and commercialized, so it depends on the developer. But the final thoughts, I think, specific to CSP, I think, as Craig had mentioned, the solar program in the U.S., we have funded a lot of projects in all of the subsystems for CSP. There remain some challenges for, the source for very high temperatures. There remain some challenges for reducing the cost of the collectors, which are still the largest contributor to the cost of the plant. We have projects on thermal storage. We have projects on power cycles. I think, if you want to get a sense of what we are doing, I would suggest that we go to our website. It's energy.gov/SunShot. It's it should be in the slides I presented. And you will get a flavor of all the different types of projects that we fund. And, so if you have any questions, you also could reach out to us.
Okay, well, we don't have time for more. I've just seen that somebody launched a question. Oh, Rodrigo's like putting his hand up. I'm going to have to let him speak.
1 minute. 1 minute.
Okay.
We have connected like the biggest or maybe the rock stars in CSP. We see Eduardo Zarza and also David Kearney here. So thank you. You are the one that has brought CSP to the world. So help us to continue this path. Thank you.
Yes, correct. We have some heavyweights. We have a lot of other good friends through the years. You know who you are: Eric, Giuseppe, Raymond, Rodrigo, Bill. These are just some of the names that I could easily identify that you are connected right now. Thank you very much, all of you, for being there. Also, thank you very much to all our dear speakers, Rodrigo, Craig, Andrew, and Angel. One of our attendees called Xavier was saying, we should do more of this. I do agree, we should. There's a lot of information that we can all learn. We appreciate all of you being here. We understand that this is a challenge, but together I think it is one that we can definitely reach. Thank you very much for your time, and I hope to see you soon again. Thank you.
Thank you.